Hello. Today we're covering factor analysis, the statistical method that finds the hidden dimensions in your survey data. When you ask people a long battery of attitude questions, many of those questions are measuring the same underlying thing without you realizing it. Factor analysis finds those patterns, groups the related items together, and reveals the core dimensions that explain what respondents are actually telling you. By the end, you'll understand how it works, how to read the output, and how to use the results. Let's start with the problem. Here's the challenge with a long survey battery. You've designed 15 attitude items to measure how consumers feel about a brand. The data comes back and you have 15 separate variables to analyze. Some of them seem like they're measuring the same thing. Trustworthy and reliable and keeps its promises all sound similar. But which ones actually cluster together? And how do you reduce 15 unwieldy variables into something manageable that you can use in further analysis? Factor analysis is a tool that answers both questions simultaneously. Here's the core insight that makes factor analysis intuitive. When people answer a battery of survey items, they don't treat each item independently. They carry underlying attitudes, and those attitudes shape their responses across multiple items at once. Someone who thinks a brand is fundamentally trustworthy will score trustworthy, reliable, honest, and keeps its promises all high, because the same underlying belief is influencing all four responses. Factor analysis finds those patterns, items that move together because they're driven by the same underlying dimension, and groups them accordingly. Factor analysis is a statistical method that identifies a smaller set of underlying dimensions, called factors, that explain the patterns of correlation across a larger set of survey items. Instead of analyzing 15 separate variables, you end up with 3 or 4 or 5 factors, each representing a distinct underlying dimension that multiple items are measuring. Those factors are cleaner, more interpretable, and more useful in further analysis than the original items. The method doesn't create information, it reveals structure that was already there in the correlation between items. Let's make the intuition concrete. Imagine a consumer who thinks Oatwave is a trustworthy brand. When they fill out the survey, they'll strongly agree with this brand is trustworthy. They'll also strongly agree with this brand is reliable, because reliability is part of what trustworthiness means to them. And they'll agree with this brand keeps its promises, for the same reason. All three items are being driven by the same underlying attitude, credibility. Factor analysis detects this by measuring the correlations between items, and items that are highly correlated with each other are almost certainly measuring the same underlying thing. The correlation is the signal. The underlying dimension is the cause. There are two versions of factor analysis, and they're used in different situations. Exploratory factor analysis, EFA, is used when you don't know the factor structure in advance. You let the data tell you how many factors exist and which items cluster onto each one. It's the discovery version. Confirmatory factor analysis, CFA, is used when you already have a hypothesis about the structure and want to test whether the data confirms it. It's the validation version, and it's more technically rigorous. For most market research applications, and for Oatwave's brand battery, EFA is the right starting point. They want to discover the structure, not confirm an assumption. Let's ground this in a real scenario. Oatwave is a plant-based oat milk brand that has designed a 15-item attitude battery for a consumer survey. The items cover a range of brand perceptions: trustworthiness and reliability, emotional warmth and excitement, affordability and value. The team had an intuition that these 15 items are measuring 3 underlying dimensions. But intuition isn't enough. They want the data to confirm the structure and to tell them precisely which items belong to which dimension. That's exactly what factor analysis will do. Factor analysis starts with the correlation between every pair of survey items, a matrix that shows how strongly each item relates to every other item. Values close to 1 means two items are highly correlated. When one goes up, the other goes up too. Values close to 0 means the items are unrelated. Knowing how someone answered one tells you nothing about how they answered the other. When you look at the correlation matrix, you can often already see clusters, groups of items that correlate strongly with each other and weakly with items outside their group. Factor analysis formalizes those clusters into factors. The first question of the analysis answers how many factors to keep. The output includes a set of eigenvalues, one for each possible factor, that measures how much the total variation in the data each factor explains. A large eigenvalue means the factor captures a lot of the story in the data. A small one means it captures very little. The standard decision rule is to keep factors with eigenvalues above 1. The scree plot makes this visual. It shows eigenvalues declining as you add more factors. And there's typically a bend in the curve where they stop declining deeply and flatten out. Keep the factors before that bend. For oat wave, 3 factors have eigenvalues above 1, and the scree plot bends clearly after factor 3. 3 factors it is. Here's the core output of factor analysis, the factor loading table. Every survey item has a loading on every factor, a number between -1 and +1, showing how strongly that item relates to that factor. A loading above 0.5 or 0.6 in absolute values means the item belongs to that factor. It's measuring what the factor is measuring. A loading close to 0 means the item doesn't belong to that factor. What you're looking for is a clean structure. Each item should load high on one factor and low on all the others. When you see that pattern, you have a well-structured battery where each dimension is measuring something distinct. Let's look at OatWave's factor loading table actually shows. The 15 items organize into 3 clear groups. The first cluster, loading high on factor 1, includes trustworthy, reliable, keeps promises, honest, and consistent. The second cluster, loading high on factor 2, includes exciting, I feel a connection to this brand, makes me feel good, inspires me, and I'm proud to use it. And the third cluster, loading high on factor 3, includes affordable, good value for money, worth the price, reasonably priced, and fair. Each item loads high on exactly one factor and low on the others. That's a clean, well-structured result. Now we need to name what each cluster represents. Naming the factors is the most interpretive step in the whole analysis, and the most important one for making the results usable. You look at the items that load high on each factor and ask, what do these items have in common? What underlying concept are they all measuring? For factor 1, trustworthy, reliable, honest, keeps promises, consistent, the common thread is clearly credibility. For factor 2, exciting, connection, feel good, proud, inspiring, the common thread is emotional appeal. And for factor 3, affordable, good value, worth the price, fair, the common thread is value perception. The algorithm doesn't provide these names, you provide them based on what the high loading items share. Once you've named the factors, you can calculate a factor score for each respondent on each dimension. A factor score is essentially a weighted average of the items that load on that factor. It summarizes how each person rates the brand on that underlying dimension in a single number. For OatWave's respondents, this means each person now has 3 scores, a credibility score, an emotional appeal score, and a value perception score. Those 3 scores are far more manageable than 15 individual item responses, and they're the variables you use and everything that comes next: regression analysis, segmentation, tracking over time, or comparing across demographic groups. Here's what the analysis actually tells O-Wave. When you average the factor scores across all respondents, 3 numbers emerge. Credibility, 4.1 out of 5. Strong. Consumers clearly see O-Wave as a trustworthy, reliable brand. Emotional appeal, 3.3. Moderate. There's some connection, but it's not strong or consistent. Value perception, 2.6. Low. Consumers don't feel O-Wave delivers good value for the price. In 3 numbers instead of 15 items, the strategic picture is clear. The brand is trusted but not exciting, and its pricing isn't landing well. That's a focused, actionable readout. And as a bonus, the clean factor structure validates the battery design. The items the team intended to measure the same dimension did, in fact, cluster together. Let's be balanced. The strengths of factor analysis. It dramatically reduces complexity. 15 items become 3 meaningful dimensions without losing most of the information. It validates survey design by confirming that items measuring the same construct actually cluster together. It produces factor scores that feed cleanly into regression, segmentation, and tracking. And it's widely used and trusted across brand research, psychology, and scale development. The limitations: it requires enough sample, typically 5 to 10 respondents per survey item for stable results. The naming of factors requires judgment, and 2 analysts might interpret the same factor differently. It assumes linear relationships between items. And in exploratory mode, it can find structure and noise when samples are small, which is why you always validate the factor structure with a separate sample before treating it as definitive. 6 things to take with you. Items that correlate with each other are measuring the same underlying dimension. That's the foundational insight the whole method rests on. Factor analysis groups those items into factors automatically based on their correlation patterns. The factor loading table shows you how strongly each item belongs to each factor. Look for high loadings on one factor and low loadings on all others. Name each factor based on what the high loading items have in common. The algorithm doesn't name them, you do. Calculate factor scores to turn the dimensions into usable variables for regression, segmentation, or tracking. And use EFA to discover structure when you don't know it yet. Then use CFA to confirm and validate it with a new sample before building it into your research program. Thank you for watching.